So now we have had something about the dot product. Now comes the cross product. This looks complicated. In a sense, it is, I would say. So we now have the cross product. So the definition of the cross product of two three-dimensional vectors. And this cross product is only defined in 3 dimensions. One can also make it a definition that sort of makes sense in 0 dimension and in 7 dimensions, but it's sort of not of any practical relevance. So we have a cross product of two three-dimensional vectors, one vector A, which we write like this, one vector B, which we write like this. So it's the formal determinant. I'll get back to what I mean by that. Given by this, I mean, this is a formal determinant. What this means is this. So here we have the vector A, and then we write this cross, and then B. That's why it's called the cross product. And then you can see here that this has to be defined, this has to be defined, this has to be defined, and then what we have in front here, not in front, after here, are the unit vectors in the three orthogonal directions following the positive directions of the axis, right? So if this is the x-axis, then we have our I vector here, our j vector here, and our k vector here, and then we should multiply them by whatever this is, and this is then just defined to be this. So the reason why this is called a formal determinant is because, as you will see later in this course, there's something called a matrix, and a matrix has a determinant, and for 3 by 3 matrices, the determinant is defined by like this, but for a matrix, these are not vectors but numbers. So it has the same structure as a determinant, but it really isn't, because what we have on top here is not a number but a vector. So let's try being concrete. Let's take one vector 3, minus 3, 2, another vector 2, 2, minus 1. Then if we take this cross product, we should write I, j, k, 3, minus 1, 2. Where does this come from? Well, it just comes from our A vector here, right? 2, 2, minus 1 comes out from our B vector. And then we should expand it like this. So we write, so the I is here, and then we take this here and make a 2 by 2 determinant. Minus 1, 2, 2, minus 1, 2, 2, and so on. So for the j, we take this column and plug in here. For the k, we take this and plug in here. And then calculating these, so the reason why I say minus 1, 2, and 2 is because you usually say it's this number times this number minus this number times this number, so that you get this. So minus 1 times minus 1 is 1, minus 2 times 2, that's minus 3, right? Times the I vector, so we should have a minus 3 at the first component. 3 times minus 1 is minus 3, minus 2 times 2, that's minus 4, minus 3, minus 4, that's 7, then there's a minus in front here, so we just get a 7 at the second component. And lastly, we have 3 times 2, that's 6, minus 1 times 2, that's plus 2, so 6 plus 2 is 8, times the k, so we get an 8 at this third component. Okay, so what is the point with this cross product? There are a few different points, like with the dot product. The first and maybe most interesting thing is that if you take the cross product of two vectors, then you get something which is perpendicular to both A and B. So here you have a vector pointing in in this direction. Here you have a vector pointing in this direction. And then you get our cross product here. And if you can see it, this is a straight angle, and this is also a straight angle. I can try moving this around, and you will see that you keep having straight angles between A and the cross product and B and the cross product. Right? So the second thing is that if theta is the angle between A and B, then the cross product has length equal to length of A times length of B times now sine of theta. So it looks a bit like dot product. In the dot product you find length of A, length of B, cosine. Right? Here you have sine. And note that since the angle is between 0 and pi, sine of theta is non-negative. So this is always a positive or at least non-negative number. So the third result is that if the cross product is non-zero, so can we make this non-zero? Well, it's can we make this 0? It's actually a bit hard. I have to yeah, it's a bit hard to to get these aligned in the right way. But if this cross product is non-zero, then the vectors A, B, and A cross B form what is called a right-handed triple. So a right-handed triple is basically if you take your right hand and use your left hand to write on your right hand, then you put an X on your middle finger, Y on the index finger, and Z on the thumb. Then they will form a right-handed triple. So in other words, if you have these two vectors, the A and B as your middle and your index finger, then your thumb should be perpendicular to it and be equal to your, in some sense, or point in the same direction as your thumb. So the last result we'll mention now is that if you have two vectors A and B that are parallel, this is what I tried to make my vectors here. Maybe I should do something like this, move it up. It doesn't work out for me, apparently. If you have two vectors that are parallel, then the cross product is 0. It's clear from this. But it also works the other way around. So in other words, this cross product is 0 if and only if the two vectors are parallel. So parallel means pointing in the same direction or the opposite direction. And again, you should remember that the 0 vector is by definition parallel to any other vector. This also makes this work in all cases.